Hi Chem students, it's Ms. Horn and welcome to a tutorial over chemical reactions part 2. Please have out your notes, a highlighter, and a periodic table. I'm going to start by reviewing from Chemical Reactions 1. Your diatomic elements are very important to remember when you're writing chemical equations. So these 7 diatomic elements form a 7 on the periodic table, with the exception of hydrogen being on the other side over here. Those are iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. You can use the little saying, I bring clay for our new hut, or just remember that makes a little 7 on the periodic table. Something else I want to make note of is that even though these are elements, the correct term for their particles is molecule, not atom. These are 2 nonmetals bonded together. Okay, a single atom would just be Br, 1 bromine. But because there's 2 of them, it makes it a molecule. Some other things we need to review are symbols used in chemical reactions. So if something is a solid, you put it in parentheses and put an S. Liquid, L. Gas is G. If something's dissolved in water, it is called an aqueous solution. So you label it AQ. This is something that kids seem to forget. Okay, so the substance is dissolved in water, it is a solution, and we label it aqueous, AQ. Plus signs will separate 2 reactants or 2 products, and you read it as reacts with on the reactant side, and you read it as and on the product side. We'll see some examples of this in a moment. An arrow separates your reactants from your products, reads as yields or produces. And then if you have a triangle on top of your arrow, this means that heat is added to the reactant as a catalyst. Catalysts are substances that increase the rate of the reaction but are not used up themselves. The formula for catalysts are written above the arrow. For example, manganese oxide. In this reaction, as we can see, it's written above the arrow. So it doesn't react with anything. The atoms are not rearranged, broken apart. Nothing happens there. It's just actually used to speed up the reaction by lowering the activation energy. Okay, so on to some new stuff. Interpreting balanced equations. It's really important for you to know when you write out a chemical reaction what each little part means. So it says the coefficient will tell you the number of atoms, molecules, or formula units of that element or molecular compound or ionic compound used or produced in the reaction. The coefficient also tells you the number of moles of the element or compound used or produced in the reaction. So that means we can interpret a balanced equation in 2 ways. So I have those 2 different ways written here for you. The first way says 4 atoms of solid iron react with 3 molecules of oxygen gas to produce 2 formula units of solid iron 3 oxide. So this is the correct way to interpret this chemical reaction. So this is kind of the opposite of what we did in the fall. In the fall, I gave you the sentence and I had you write out the reaction. Well, now I'm giving you the reaction and having you write it out as a sentence. Another way that you can interpret this is in the mole form. So these coefficients also stand for how many moles of the substance you have. We call this the mole ratio, and that'll be more important to you when we get to stoichiometry, but it's good that you understand it now. Okay, so you can also read this as 4 moles of solid iron reacts with 3 moles of oxygen gas to produce 2 moles of solid iron 3 oxide. For example 2, I want you to try this one on your own. So please pause the video, and once you unpause, I will give you the answer. All right, welcome back. So the answer for example 2 is 1 atom of solid carbon reacts with 1 molecule of oxygen gas to produce 1 molecule of carbon dioxide gas. Or you can write it in mole form. 1 mole of solid carbon reacts with 1 mole of oxygen gas to produce 1 mole of carbon dioxide gas. Okay, so moving past review material, we're going to learn about the 5 types of chemical reactions in this video. There are more types, but that's beyond the scope of this class. We're just going to learn about these 5: synthesis, decomposition, single replacement, double replacement, and combustion. Our first type of reaction is synthesis reaction, also called combination or composition. So synthesis means to put together. This is when two or more elements or simple compounds combine in order to form one compound. So the general form here is A plus B yields AB. So these are separated on the reactant side, but you have one product on the product side. The identifying feature is that there is only one product. An analogy that we'll use, and you'll see these analogies in your practice packet, is a boy and a girl come to the dance separately, but end up dancing together. A real life example is when you've got magnesium and oxygen reacting on the reactant side to produce magnesium oxide. Okay, the next type of reaction we're going to talk about is decomposition, which means to break apart. In this reaction, one compound is broken down into two or more simpler elements or compounds. And the form, if you look at it, it's the opposite from synthesis. You've got AB together yields A plus B. So the identifying feature in decomposition is there's only one reactant. Again, I'm going to emphasize that this is the opposite of synthesis. So our analogy here is a boy and a girl come to the dance together, but they argue and stay apart for the rest of the night. So decomposition is like our breakup reaction. I've got a couple examples listed here. They are worth writing down. So sodium chloride decomposes to form sodium plus chlorine. Or potassium chlorate decomposes into potassium chloride and oxygen. Okay, our third type of reaction is single replacement. In this situation, one element takes the place of another in a compound. And notice I've written here like replaces like. So what does that mean? Well, if you look at our general forms, I've got A plus BC. So this is a single element plus a compound. Reacts to form B plus AC. So what happened here is that A and B actually switched places. Okay, and this would be an example of metal replacement. That's why it's like replaces like. So two metals can switch places, or like in the next example, two non-metals or halogens, to be more specific, can switch places. The identifying feature for this one is one element in a compound on each side of the arrow. So our analogy is a boy and a girl are dancing, but then another boy cuts in and dances with the girl, leaving the first boy alone. Or a boy and a girl are dancing, then another girl cuts in and dances with the boy, leaving the first girl alone. But notice here that you always have a boy-girl couple. And the reason for that is because like replaces like. Boys are going to switch out with another boy, or girls are going to switch out with another girl. Just like in our real examples in chemical reactions, metals will trade places or halogens will trade places. So I have an example of the metal replacement. We've got sodium plus copper to chloride react to form sodium chloride plus copper. So you can see here that the sodium and the copper switched places because now sodium is with chlorine, not copper. And copper is all by itself. In the next example, I've got the halogen replacement. So we've got fluorine and chlorine switching places so that potassium and fluorine are together and chlorine is by itself. This is called single replacement. So something interesting about single replacement is that it doesn't always occur. Sometimes the answer might be no reaction. Well, why is that? It says here, the boy-girl will not always be able to cut in. Sometimes the other boy or girl will not let them. In a chemistry reaction, we use an activity series to predict whether or not the replacement will occur. If an element is more reactive then another element, it can replace that element. So it actually has to be above it on the activity series in order to replace it. So here's our activity series. This is not something that needs to be memorized. I will actually give this to you. For example, if we are trying to see if zinc will replace tin. Yes, it will. Zinc will replace tin because it is higher, meaning it's more reactive on the list. So as long as it's above the other element, it can replace. But if tin was trying to replace zinc, because tin is below it, the answer would be no reaction. This actually is not possible. Okay. For our halogens, this is the same order as on the periodic table. Fluorine is the most reactive, iodine being the least. So it also increases going up just like it looks on your periodic table. So let's look at some examples here. Can copper replace gold? All right, well, up on my list, copper is here, and gold is at the very bottom. So the answer would be yes. Copper can replace gold. Why? Because it's higher on the activity series. Can bromine replace iodine? Why, yes, because bromine is up here, iodine is down here. And then lastly, can chlorine replace fluorine? Well, the answer would be no, because chlorine is lower than fluorine on the activity series. So the answer for that one is no. So realize I'm going to give you the activity series for metals. You do not have to memorize these, but for halogens, you do have to realize it's the same as the order on your periodic table. The ones at the bottom are least reactive, the ones on top are the most reactive. It says, note, the activity series is only used for single replacement reactions only. Okay, the fourth type of reaction is double replacement. This is a situation in which ions from two ionic compounds are going to switch places. So the general form is AB plus CD yields CB plus AD. It says A and C, the cations from each compound switch places. So you can look at it that way, where these two switch places. So now A and D should be together, and B and C should be together. For me, I like to look at it a little bit differently just because I'm a really visual person, and I use what I call the box method. What I do is I box in the inner two, and I say that the ones inside the box are going to react to form a new compound, and then the ones outside the box react to form a new compound. For me, it's just a more visual way to see it, and I like it better. So either way is totally correct, whatever's more easy for you to remember. So the identifying feature is that you'll see two compounds on each side of the equation. Our analogy is two boy-girl pairs are dancing and they switch partners. So you can see originally we have the non-accessorized couple, and then on the reactant side we have the accessorized couple, and then they just switch partners, like the boys trade places. So we see the guy with the hat dancing with the plain girl, and then the boy that's plain dancing with the accessorized girl with the bow on her head. So basically the boys just traded places here. A real-life example is iron 2 chloride reacting with sodium carbonate to form sodium chloride and iron 2 carbonate. So again, the box method makes this really easy to see. Now you can see iron and carbonate are together and sodium and chloride are together. The one thing to remember about this method is that the metal always has to be written first. So inside the box, you've got to write the sodium first and then the chlorine, because your metal has to be written first in a compound. All right, a type of double replacement reaction is called neutralization or acid-base reaction. It's a special type of double replacement reaction. It occurs when an acid and a base react to form an ionic compound known as a salt and water. So your reactants are acids and bases. Your products are salt and water. So for example here, we've got hydrochloric acid reacting with sodium hydroxide. Using the box method here, it's very easy. I've got sodium chloride forming and water forming as well, because hydrogen and hydroxide form H2O, water. Another example is sulfuric acid and potassium hydroxide using the box method. Water, again, is formed on the outside, so anytime you see hydrogen and hydroxide, that is the formation of water. And then inside, I've got potassium and sulfate, so it's going to be K2SO4. Easy. The last type of reaction we're going to talk about is the combustion reaction, also known as burning. It's always going to follow the same form. So you have a compound containing carbon and hydrogen. Sometimes it'll have oxygen. Now this compound is called a hydrocarbon because it contains carbons and hydrogens, plus oxygen, and you'll yield carbon dioxide and water, always. It says, no, in a combustion reaction, the compound always burns in oxygen gas and always releases carbon dioxide and water. During incomplete combustion, there's a limited amount of oxygen. Carbon monoxide will be produced instead. So that is a possibility in an incomplete combustion reaction. So in our examples, I've got methane plus oxygen gas produces carbon dioxide and water. And another hydrocarbon right here plus oxygen yielding carbon dioxide and water. So notice carbon dioxide and water are always our products. You have the presence of oxygen and some form of hydrocarbon right here. With combustion reactions, they can be very tricky to balance. So I do have a little trick for you here. It says you want to balance the hydrogen first by placing a coefficient in front of water. If that coefficient is odd, double it and proceed with balancing carbon, then oxygen. Always balance oxygen last. So the big trick here is that in front of the water molecule, you cannot have an odd number. So for example, on the left side, I have 14 hydrogens. So I want to put a 7 here, but I can't because 7 times 2 is 14, right? I can't because that's an odd number. So I'm going to double it. Instead of putting a 7, I'm going to put a 14. So that means there's 28 hydrogens on the product side. To make up for that, I'm going to put a 2 in front of the hydrocarbon. And this ends up working out in the long run. So after you've balanced out your water molecule or your hydrogens first, then you want to move on to doing carbons. Remember, oxygens are very last. So I've got 14 carbons because 7 times 2 is 14, which means I need to put a 14 in front of carbon dioxide on the product side. Lastly, I'm going to add up my oxygens. So I've got 28 plus 14, which gives me 32 oxygens. So I'm going to put a 16 in front of O2 on the reactant side. So again, a trick for balancing combustion reactions is to make sure that the number in front of the water molecule is an even number. I hope you enjoyed today's video. In our next video, I'm going to teach you how to predict the products of these reactions. For now, all I need you to know is how to recognize them. I look forward to seeing you in class tomorrow to practice some more. Have a good evening.